How you doing, kids? This is Stats with Glenn, Chapter 7. Chapter 7 is all about hypothesis testing if n equals 1. Now, I will tell you that when I wrote the book, I intentionally divided hypothesis testing into chapters 7 and 8. Hypothesis testing with an n of 1 is actually a very rare situation. However, you will find that the math associated with hypothesis testing, if n is greater than 1, is a lot more complicated. And hypothesis testing is already somewhat complicated. So this is why chapter 7 is all about hypothesis testing if n equals 1. And as we progress during this lesson, you'll see what that even means, n equals 1. But here we are, 4-2. The year is 2020. This is the year of the crazy coronavirus, kids. We're gonna get through it. We're gonna be fine. Just like to put that out there as a public service announcement. But so here we are, April 2nd, and chapter 7. Hypothesis testing if n equals 1. Okay, let me give you an example. I've got some numbers in the textbook, actually. I'll just throw these numbers out here. So imagine a scenario. Imagine you're teaching stats. One day you could be teaching stats. And imagine you do a study. You have 2 sections, and you want to see if doing the homework is helpful. I know I assign a ton of homework in stats, and I don't do that to be mean, in case you were wondering. I do that because I think it is very helpful in having students learn the material. But imagine you did a study to see, is that actually the case? So imagine you have 2 groups. You have textbook only, and then you have kids who read the textbook plus they do the homework. So imagine half the kids are doing the textbook, half the kids are doing the homework and the textbook reading. And I've got 4 students in each section. It's a fancy private school, and we're allowed to only have 4 students in each section. We can dream. Just kidding. Love all my students, by the way. Textbook only. So here's the scores on the exam. This group, we get an 80, a 75, 76, and an 88. In the textbook and homework condition, we get a 76, a 90, an 84, and an 82. Okay. Now, the question, and this is a question that pertains to inferential statistics more generally. The question is there a difference? Do I have data here that can inform future practices? Do I have data here saying whether it's better to read the textbook and do the homework, or is there no difference? Because if there's no difference, to be honest, then I might as well tell students there's some homework problems, but the research shows it doesn't matter if you do the homework problems or not, right? So this is the kind of statistical test that can address that particular kind of question. You've been sitting in this class long enough so that when you see numbers like this, you probably are yearning for the mean, right? The first thing you really want to know in terms of central tendency is what is the mean for this group? What is the mean for this group? Look at that, kids. Page 140, right there. The mean for this first group is 79.75. And the mean for the second group is 83.00. Okay, I'm gonna stop right there. Think about it. Question number 1, is there a difference? Is there a difference between the groups? And related, is the difference in the direction that we kind of are expecting? That the kids who read the textbook and do the homework are doing better and are the kids who are just reading the textbook? Well, the mean for the kids who do the textbook and the homework is 83. The mean for the kids who read just the textbook is 79.75. 83 is higher than 79.75. If you were a student in this class, you'd prefer to get a grade like 83 in the B- range than 79.75, which is kind of a little more like the C+ range. Does it look like doing the reading and the homework is better than just the textbook? Prima facie. You want a Latinism, kids? Whether you want it or not, there it is. Prima facie, on the surface, it looks to be the case. It looks to be the case that textbook and homework is superior, on average, to just the textbook. However, if you're skeptical, and I hope you are, because all college students should be skeptical, college is kind of a lesson in skepticism, if nothing else, you're probably scratching your head saying, oh, gee, Glenn, those numbers are different, but they're not that different, right? 83 is only a little bit higher than 79.75. A. And then B, you're probably thinking, this is a dumb study. This study has 4 people in each condition. That is what we call a small n, or a small sample size. What is the point of inferential statistics? We are trying to make inferences based on sample data to broader populations of interest. Who's the broader population of interest here? All the potential statistics students in the world who read the textbook versus all the statistical students in the world potentially who read the textbook and who do the homework. Are these data compelling enough for me to get on the phone with my mom right now and say, Mom, I found something amazing. I found great evidence that students who read the textbook and who do the homework do significantly better than students who just do the textbook. Do I have the basis to make that claim? In short, I do not. I do not yet, and I probably will never have that with these data. So this is what hypothesis testing is about. It's not just eyeballing data, it's not eyeballing numbers, it's not just looking at numbers saying, yeah, here's what it looks like. It is a very systematic process to figure out whether some pattern found in a sample likely generalizes to a broader population of interest. So we're going to go through the 5 steps of hypothesis testing. Okay, so we're going through the 5 steps of hypothesis testing. Number 1, we're going to articulate our hypotheses. We are going to articulate what I'm going to call H sub 1 and H sub 0. H sub 1 is shorthand for what we call the research hypothesis. The research hypothesis is the hypothesis that is guiding the research. It's the guess that the researcher has. It's what the researcher thinks is the case. Okay, so I'm going to use as an example, because we've kind of already gone with this as an example, I'm going to use as an example, does doing the homework in stats lead to better grades? My prediction is that doing the homework, in addition to everything else, doing the homework leads to better grades, or reframe it, the population of students who do the homework has a mean in terms of their grade that is greater than the mean for the general population. Now, that might sound a little confusing, but I will articulate that out for you. So, these are the 5 steps of hypothesis testing. Before we get into it, I'm going to do a little bit of a sidebar. Okay, and I'm going to put up what I call the difference between sample versus population parameters. Because in hypothesis testing, we're taking data from a sample, we're making an inference to populations. So here we have what I call sample versus population parameters. So we have sample versus population parameters. It didn't matter up until this point. Up until this point, we were a little bit loosey-goosey. We talked about the mean, we talked about the standard deviation, the variance. Here, it matters what symbols we use. So we have the mean, the variance, and the standard deviation. Okay, so those are 3 things that we will be talking about. The mean, when we were talking about a sample, chapter 2, chapter 3, etc. For the mean, we use the symbol M, capital M, meaning the mean. If we're talking about the mean of a population, and when we're doing inferential stats, we're thinking about means of populations. We're now, instead of M, going to use this Greek symbol that looks like this. Statisticians pronounce it mu. If you want a weird little sidebar, I had a Greek kid in my class one time named Demetrius, and when I called that mu, he laughed his head off because he said, that is not how you pronounce that, and every Greek person in the world knows that. And I said, Demetrius, this is how statisticians pronounce it, and we had a minor disagreement in front of everyone. And I will tell you, to Demetrius's defense, he's probably right because that dude's Greek, and he pronounced it meh, like almost like M-E-H. Does that matter for your purpose? No, because statisticians pronounce that mu. No clue why. Someone probably mispronounced it a long time ago, and you know how things go. In any case, this symbol that we call mu means the mean of a population. You'll see it's relevant because when we are articulating our hypotheses, we articulate our hypotheses in terms of populations. We are making predictions not about samples, we are rather making predictions about populations. So mu means the mean of a population. You'll see we're going to get a little more fine-grained regarding mu, but just for now, mu means mean of a population. The variance, you remember our friend the variance? For sample, the variance was SD squared, which essentially means the standard deviation squared. If we're talking about a population variance, we're going to get this symbol here. This little guy, isn't that a cute little Greek symbol, kids? I call it baby sigma. Remember we had big, bold sigma, kind of looked like a big capital E. It meant sum of, and you didn't want to mess with that particular symbol. This is baby sigma. So remember I said case matters, uppercase, lowercase. Lowercase sigma squared represents variance at the population level. Standard deviation at the sample level, we have already talked about that. That's SD. And standard deviation at the population level is simply baby sigma. These are all things that are articulated on page, looks like page 142 in the textbook, and they will start becoming very relevant very quickly. So there's your sample versus your population parameters. Highly relevant for step number 1 on hypothesis testing. Remember, step number 1 on hypothesis testing is you're articulating your research hypothesis and your null hypothesis. Your research hypothesis is the hypothesis that you have that is driving your research. I, as a researcher, predict that students who do their homework get higher grades on average in stats compared to the general population of statistics students. Okay, so when I articulate that, I'm going to articulate that in terms of this symbol, H sub 1. H sub 1 means the research hypothesis. Before I articulate the research hypothesis, I'm going to say what mu sub 1 is, and I'm going to say what mu sub 2 is. Mu sub 1 and mu sub 2 are means of populations. Mu sub 2 is the mean for the general population. So I'll just write general pop. Okay, so mu sub 2 is the mean for the general population. And mu sub 1 we will use, it's kind of arbitrary, but here's the system we're going to use in this class. Mu sub 1 represents the mean for the special population. Who's the special population in this case? It is the population of students who do their homework. So if you're a student who does your homework, consider yourself special in a good way. So this is the homework students. Mu sub 1 is the mean on the stats exam for the homework students, and mu sub 2 is the general population of statistical students. For chapters 7, 8, and 9, all of our examples are going to be comparing a special population relative to a general population from which the special population is drawn. That is for logistical purposes. Once we get to chapter 10 and beyond, we will get to more realistic situations where we're comparing two different populations against each other. But here, for now, for this chapter and the next few chapters, we're dealing with a situation of comparing a mean of a special population from a general population that the special population is drawn from. Okay. So now in terms of symbols, let's go back to articulating our research hypothesis and null hypothesis. H sub 1 is our research hypothesis. Mu sub 1 greater than mu sub 2. Okay, do you see this simple little thing I just underlined right there? Mu sub 1 is greater than mu sub 2. Given that mu sub 1 is students who do homework, mu sub 2 is the general population. So this little phrase, this little set of mathematical operations simply is saying that we are predicting. You remember, the real world, our predictions are not always right. That's the whole reason we do stats, right? If our predictions were always right, we wouldn't need college, we wouldn't need statistics, we could just make predictions and say my prediction's right. Not how the world works. So this is just a prediction. Here, the prediction is that the mean on the stats exam for the students who do homework is greater than is the mean for the general population. H sub 0. This is also called the null hypothesis. The null hypothesis. The null hypothesis, as opposed to H sub 1, which again is the research hypothesis, the null hypothesis, the best way to put it is if the null hypothesis were a person, it would be a jerk. The null hypothesis is disagreeable. The null hypothesis is not your friend. The null hypothesis is someone in your world who, when you say something, says, you're wrong. And not only does the null hypothesis say you're wrong, but the opposite of what you think is right, if anything. So the null hypothesis is kind of a jerk of a hypothesis. I'll tell you what the null hypothesis is. A, it is the opposite of the research hypothesis. So mu sub 1 less than mu sub 2, right? It's kind of saying, if anything, students who do homework do worse, lower than the general population. the null hypothesis always has an equal sign in it. So it will always have an equal sign, and it will always be the opposite of your research hypothesis. And when we're hypothesis testing, just to kind of step back and think about the bigger picture, what we're actually testing is whether the equal part of the null hypothesis is very unlikely to be true. So the bottom line of what we're doing hypothesis testing wise is asking that particular question. So we're not testing the research hypothesis, we're actually testing the equal part of the null hypothesis. Step number 1, articulate the research and null hypothesis. Step number 2, we're going to come up with what we call a comparison distribution. The comparison distribution is a distribution that assumes that the equal part of the null hypothesis is true. So if the equal part of the null hypothesis is true, then that means, I'm going to draw it over here, that means that mu sub 2, the mean for the general population, is the same as mu sub 1. So the null hypothesis is assuming, I'll draw 2 universes real quick. Here's one universe. One universe is the research hypothesis is right. If the research hypothesis is right, the mean for the special population, students who do homework, is greater, shifted to the right, than the mean for the general population. However, if the null hypothesis is correct, or if the equal part of the null hypothesis is correct, then mu sub 1 equals mu sub 2. So we're kind of testing to see if it's really unlikely that mu sub 1 equals mu sub 2. So this reality here is essentially the equal part of the null hypothesis, and that is what we are testing. So in doing that test, we have a comparison distribution. Our comparison distribution for that test is the distribution for the general population. In a hypothesis testing example, you're going to be given some information. So I'm going to give you that information right now, the information that will be what we call given information. Okay, first off, we're going to get mu sub 2. I'm going to put mu sub 2 as 80. We could put that down here. Okay, I'm going to give you sigma sub 2. Sigma sub 2 is the standard deviation for our comparison distribution. I'm going to put that at 5, assuming the population level standard deviation for scores on the exam is 5. There's another piece of information I'm going to give you, but I'm going to hold off on it. There's a couple other pieces that I'll give you, but I'll wait until they're sort of relevant. So here's our comparison distribution. It assumes the equal part of the null hypothesis is true, and it has a mean of 80, and it has a standard deviation of 5. Step number 3, we're going to have something that I call Z critical, or Z crit. Okay, the Z critical, sometimes called the Z cutoff. Here's what it does. It sets up a special section of your comparison distribution. it sets up a part of your distribution that you are a priori, that's Latin for ahead of time, that you are a priori defining as really unlikely to come about by chance. You remember with normal distributions, scores that are way out in the tails are very unlikely. So what we're doing with our z-critical is we're going to find a critical value that has a probability associated with it that is so low that later when we get an actual z-score from the special population, we'll see if it's more extreme than this critical value. So that's kind of what we're moving toward. So z-critical. Z-critical is based on an alpha. Okay, it's based on an alpha. So that little baby alpha right there. Alpha is a section of your distribution, or section of your comparison distribution, that you are defining as incredibly low in likelihood, and you are defining it ahead of time. If you don't define it ahead of time, then you can kind of just make up the rules as you go along. So this is the fact that we make it, that we determine it ahead of time, is a way of controlling our own behavior as researchers. Okay, so what alpha do we go with? I'm going to give you a real short version of this. There's two alphas that researchers use. The most standard alpha, and this will be given information, is 0.05. An alpha of 0.05 means I'm going to define a section of my distribution that will happen 5% of the time or less. And so when I get my z representing my special population, if it is in that special region of alpha, which happens 5% of the time or less, then I'm going to step back and I'm going to say that's very unlikely to have come out of this distribution. I can reject that the score came out of that distribution. I can reject the null hypothesis. So this is kind of where we're going. So we need to find an alpha. And the alpha is going to be given, and it's usually 0.05, and it is sometimes 0.01. The reasoning behind whether you use 0.05 or 0.01 is spelled out in detail in the textbook, I think about page 146. Yeah, it's described in some detail on page 146. But the alpha, let's say we usually go with an alpha of 0.05. The critical value also follows the research hypothesis. Okay, so this z critical, whatever that is, we know it defines this 0.05 low probability part of the distribution. The critical value will follow the research hypothesis. So the research hypothesis says that mu sub 1, we can imagine mu sub 1 existing above mu sub 2. Mu sub 1 is greater than mu sub 2. Therefore, we are predicting that the distribution for the special population is shifted to the right, and therefore, the critical value will follow that. So the critical value that I'm going to call z critical is going to be to the right of the mean of the general population or the mean of the comparison distribution. The sign and the placement of the critical value always follows the research hypothesis. So mu sub 1 is predicted to be greater than or to the right of the mean for the general population. So now we can take a look. These are some of the skills we developed in chapter 6. I have a normal distribution. I can divide it into A, B, and C. I have my mean. I have my particular z-score of interest. I also happen to know that C is 5%. C is 5% because that's alpha. Alpha is 0.05, which corresponds to 5%. If C is 5% of the distribution, and A is half the distribution, so that's 50% of the distribution, then section B must be 45% of the distribution. So section B is 45% of the distribution. Because 50 plus 45 plus 5 is 100. So the entire distribution is 100. That special alpha region is 5%. The part we're defining as very unlikely to be due to chance. And section B is 45%. Do you remember on page, I think it's page 325. Yeah, on page 325 we have our appendix, the Z table. We can figure out the Z critical here by looking up the Z table. Remember, the Z table has Z and percent mean to Z. Dana, I'm just gonna kind of zoom in. Let's see if we can, so you remember, the Z table has two columns. It has Z and it has percent mean to Z. We have percent mean to Z right now, which is 45%. So I'm gonna look up 45%. Mean to Z, and I find a weird situation. I only know this because I've taught this a million times. I find a weird situation where there's no 45%, there's 44.95%, and then there's 45.05%. Those are equidistant to 45%. One corresponds to a Z of 1.64, one corresponds to a Z of 1.65. I will accept either. The one that statisticians use tends to be 1.64. So right there from this column, that is where we're going to get that Z critical of 1.64. So Z critical, I'm writing it up here, equals 1.64. Here's what that means. That means that we're defining this part of the distribution, our comparison distribution. The part we're defining as really unlikely to come about by chance is this alpha region, which corresponds to section C over here. And the Z-score that cuts off that section is 1.64. So my critical Z-score is 1.64. When I get a Z representing my special population, if that Z is more extreme than 1.64, that's going to lead me to make a decision regarding the null hypothesis. In fact, that's going to lead me to rejecting the null hypothesis. So Z critical, and we're going to do another example, by the way, when we do what we call a two-tailed test, which we'll do in just a couple of minutes. And chapter 8 will have examples as well. I know that this reasoning is often considered by students to be a little bit convoluted and it's kind of novel. That's okay, we're going to go over more examples. So Z critical is 1.64, it's right over here. Step number 4 is what I'm going to call Z obtained. Z obtained is a Z-score that corresponds to a raw score that is randomly selected from the special population. So if we're going to do this test, we're going to randomly get one score from the special population. Who is the special population? Recall, it is people who did the homework. Now, usually we would get more than one randomly selected score, but again, to try to keep the math constrained in this chapter, this is what I mean by we're going with an N of 1. The next chapter, we're going to go with an N of greater than 1. So Z obtained, we're going to randomly select a score, okay? That will be part of the given information, X. I'm going to give you that as 93. Okay, so the randomly selected student in the population of students who did their homework, that one randomly selected score that we get is 93. Can I compare 93 with a z-critical of 1.64? Not yet, because 93 is a raw score and 1.64 is a z-score. Therefore, I need to convert my obtained score of x of 93, I need to convert that to a z-score. So that's what I call z obtained. It is the z-score that corresponds to my obtained raw score. Z obtained equals my particular x of interest minus the relevant mean. Instead of m, I'm going to now put mu sub 2. Okay, so we're now subtracting out the relevant mean, and the mean now is from the comparison distribution. It's the mean for the general population, and we're going to divide out by the standard deviation of the general population, sigma sub 2, which equals 93 minus 80 over 5. And my calculator is saying 2.6. Positive 2.6. Okay. So I know it's a little bit squished over here, austere conditions, kids. But if you zoom in right over here, you can see z critical is 1.64. And my z obtained is 2.6. So if I'm looking at this distribution here, if this right here is 1.64 as a z-score, then here, this is z obtained equals 2.6. So my z-score that corresponds to my randomly selected raw score for my special population is over there. Let me use some, I'm going to get a little pink out, kids. Okay, so here's the critical value. You see I just circled the critical value. This is my critical, my z critical. And here is my obtained z-score. And now the question, this is step number 5. The question now is, or the process now is I'm going to comment on the null hypothesis. Okay, so I'm going to comment on the null hypothesis. You remember, when we're hypothesis testing, we're essentially testing whether the equal part of the null hypothesis is very unlikely to be the case. If the population mean for the special population was the same as the population mean for the general population, what are the odds that I would randomly select a score from that special population that was so extreme that it was way in the tail of the distribution for the general population? Likely or unlikely? Very unlikely. So given, and in fact, it was more extreme than my z-critical. It's a simple rule, or what I call a dichotomous rule. If my obtained z-score is more extreme than is my critical score, I will reject the null hypothesis. So comment on the null hypothesis. I'm going to reject the null hypothesis. Okay, think about what that means. I'm rejecting the null hypothesis. So here's my two hypotheses. I got my research hypothesis and I got my null hypothesis. By rejecting the null hypothesis, I'm kind of saying, you're wrong, null hypothesis. Go home, we don't like you. And I am what's called supporting my research hypothesis. Importantly, and we're going to get into this in a little bit, when you support your research hypothesis, you could still be wrong. Hypothesis testing is a really tenuous business, and no matter what you conclude, you could always be wrong. So there are what we call errors in hypothesis testing, which we will discuss as the final part of today's lesson. But for now, realize that these are the 5 steps, and if your z obtained is more extreme than is your z critical, you've provided evidence that you can reject your null hypothesis and that you should be able to support your research hypothesis. So that's the basic steps of hypothesis testing. I'm going to erase this whole thing. And we're going to do another example. There's one more situation that you're going to run into. Okay, you're going to run into a situation of what we call a two-tailed test. Okay, the example that we just did is an example of what we called a one-tailed test. Okay, so we had a comparison distribution. We set up an alpha region, which was way over in that one tail, and we were only interested in the situation where the obtained z-score was more extreme than that obtained, or the critical z-score, which was in this one particular tail. A one-tail test is also sometimes called a directional test. If I'm making a prediction in a specific direction, then I'm only interested in alpha being in one tail of the distribution. Sometimes in life, we have what we call a two-tail test. With a two-tail test, you are predicting a difference between two population means, but you're not really specifying the direction. Which one's going to be higher, which one's going to be lower. Okay, so I'm going to give you an example of a two-tailed test. A two-tailed test is essentially one where you could make the case either way. It's like the special population mean could be greater than the mean for the general population, or you can make a case that the population mean for the special population is less than is the mean for the general population. I'll give you an example. So I work at SUNY New Paltz. We have great Division III athletic programs. I'm a big fan of the athletic programs on campus. But when you think about athletics and academics, there are two schools of thought. Some people make the case, or try to make the case, that student athletes do worse academically than students in general. Other people, I consider myself, based on my experience in this camp, other people might make the case that because student athletes have to organize and self-discipline so much, they actually will do better academically on average than the general population. But you could make a case either way. So that's a two-tailed test. Okay, so with a two-tailed test, and let me give you all this information. Okay, so I'm going to give you mu sub 2 is going to equal 2.5. So the GPA mean for the general population, I'm going to put that at 2.5. Sigma sub 2, I'm going to put at 0.5. Alpha, I'm going to give you as 0.05. Okay, so that's some of the given information that we're going to have. And now we're going to do a two-tailed test. You'll see that the two-tailed test is just like the one-tailed test, except slightly different at certain parts of the process, okay, including the hypotheses. So step number 1, we're going to articulate H sub 1 and H sub 0. Okay, remember H sub 1 is your research hypothesis. We are predicting a difference. H sub 0 is your null hypothesis. It is your opposite of your research hypothesis. Okay, mu sub 1 is going to correspond to student athletes. And mu sub 2 is going to correspond to students in general. Okay, so mu sub 1 is student athletes, mu sub 2 is students generally. Research hypothesis. With a two-tailed hypothesis, we now have what we call a non-directional research hypothesis, and there's two possibilities. I'm kind of saying, on one hand, mu sub 1 might be greater than mu sub 2. So the mean GPA for students in the student athlete condition might be greater than the GPA for students in general. Or, I'm actually going to write the word or if you're okay with that, mu sub 1 is less than mu sub 2. It is possible that student athletes have a GPA that is lower than is the mean for students in general. We could, if you want, you ready for this, kids? I'm going to take my finger and erase that, and we could simply put that as mu sub 1 is not equal to mu sub 2. Okay, that encapsulates mu sub 1 is greater than mu sub 2, and mu sub 1 is less than mu sub 2. Null hypothesis is always the opposite of the research hypothesis, and it always includes an equal sign. With a two-tailed hypothesis, it's real simple. Mu sub 1 equals mu sub 2. So the null hypothesis for a two-tailed test is simply saying no difference. Student athletes have a GPA that is no different than students in general. Step number 2, comparison distribution. Okay, the comparison distribution, identical as what we did with the one-tailed test. It represents our general population, mu sub 2. The mean is 2.5. That was given information, that's where that came from. The standard deviation is 0.5. That's our comparison distribution. So our comparison distribution is our distribution for our general population, and that's what we're going to be comparing against. Step number 3, Z critical. Okay, there's a little bit of a difference here. We still have alpha of 0.05. Remember, you could also have alpha of 0.01. That would be given information, but we don't. We have alpha of 0.05. The thing is, with a two-tailed test, I could reject the null hypothesis if my Z obtained is extremely high or is extremely low. Because of that, I now am going to have two critical values, two Z criticals. One in case the special population mean shows evidence of being greater than the general population mean. One in case the special population mean shows evidence of being less than the general population mean. So with a two-tailed test, that's kind of why it's called two tails. We're looking at both tails of that distribution. And alpha now will be split among or between those two parts of the distribution. So alpha is 0.05. What that kind of means is that 2.5% will be here, and 2.5% will be here. Okay, so I'm taking the 5% and I'm splitting it among these two different regions. Okay, if this section is 2.5%, then this section is 47.5%, and this section is 47.5%. Okay, because 47.5 plus 2.5 is 50, so that's how this divides up. I'm going to go back to my table, and what I'm going to look at is 47.5%, because that is the percentage between the mean and the particular z scores of interest. In this case, the z criticals, and in this case, there's two of them. So I'm looking up percent mean to z of 47.5, and looks like I'm going to go on to page 327. Here it is, kids. Do you see that right there? 47.5%, and that corresponds to a z of 1.96. So my z critical over here is 1.96. Is there just one z critical? No, there's two, because it's a two-tailed test. So z critical over here will be negative 1.96. So positive 1.96 and negative 1.96. There are two critical values. One in case there's evidence that the special population mean is very high relative to the comparison distribution, and one in case it is very low, taking both aspects of the research hypothesis into account. So z critical equals positive 1.96 or negative, plus, or what we might call plus or minus 1.96. Okay, so it's just like z critical with one-tailed, except now we're dividing alpha among these two different tails and taking that into account in determining our z critical, which we get by looking in the back of the book through that process we just went through. Step number 4, z obtained. Okay, so what we would do, just like we did in the last example, is we would randomly select one student athlete. I'm going to go into the swimming team, and I'm going to grab a swimmer. My student Brooke is on the swimming team. Brooke, I don't want to pick on you, but I'm assuming you have a good GPA because you seem like a bright kid and you're working hard. And so I'm going to randomly select Brooke, and I'm going to ask Brooke, sorry if this is ego-threatening, her GPA. And I'm going to give you a high GPA, Brooke. I hope it's warranted. But I'm going to say that X equals 3.4. So I'm randomly selected one student athlete. In this particular case, it is our friend Brooke, who is excellent in the breaststroke, if I recall correctly. And I'm going to put Brooke back so she can go back to her life. And now we have X equals 3.4. Z obtained, same formula that we used before, equals X, the random score representing the special population, minus the mean of the comparison distribution, which is represented by mu sub 2, divided by the standard deviation of the comparison distribution, represented by sigma sub 2, which is 3.4 minus 2.5 over 0.5. Calculator time, kids. I got 1.8. Dana, you got 1.8? Okay. And the answer here is 1.8. Okay. Let's take a look at our comparison distribution. So here's our comparison distribution. We can think of it as a z distribution. The mean of z is 0. This critical value over here is 1.96. This critical value over here is negative 1.96. Our z obtained, corresponding to our score representing our special population of student athletes. The raw score was 3.4. The z score was 1.8. Okay, I'm going to get out my little pink marker here. 1.8. Here's 1.96. Here's 0. A z of 0 is right in the middle. And z obtained equals 1.8. Okay, this is in hypothesis testing a kind of sad story, kids. Do you see it? I'll show it to you. So right here, to reject the null hypothesis, we needed our z obtained, representing our special population, to be more extreme than z critical. We needed it to be over here in our alpha region. Was it over there? No, it wasn't. It was almost over there, but it was not quite over there. Z of 1.8 relative to a z of 1.96. So, in that case, sorry, Brooke, I tried on your behalf. I hope you saw that. In that particular case, number 5, we're going to comment on the null hypothesis. Now, in a situation like this, where the obtained score is not extreme enough to reject the null hypothesis, we're going to write this. We're going to write fail to reject the null hypothesis. Okay, when we fail to reject the null hypothesis, another phrase for this is our findings are inconclusive. We don't know. Is it possible that because we got a sample of only 1, that we did not reject the null hypothesis? That's possible. Here's another thing for you to think about. Two-tailed test makes it harder for you to reject the null hypothesis. So we kind of move the goalpost a little bit further when we made it a two-tailed test. If we did a one-tailed test, we actually probably would have rejected the null hypothesis. Or maybe student athletes don't have a GPA that's any different than the general population mean. So we simply are stuck with the aw noodles, it's inconclusive, we just don't know kind of situation. That's okay. As someone who's 50 and has done dozens and dozens of studies over my lifetime, this is probably the most likely outcome. Students are often disappointed to find that, but I'm never surprised or disappointed because I've seen that lots and lots of times. But anyway, there you go. That's what happens when you fail to reject the null hypothesis, and that is what a two-tailed hypothesis test is like. One final thing, I believe, Dana, is that right? One final thing that we're going to talk about pertains to what we call errors in the hypothesis testing procedure. So, look at this, kids. I'm going to go 90 degrees on this one. You know what? I'm going to hold it. Look at that. This is crazy. Can we handle this, Dana? Yeah. We can handle it. Okay. And in case it sounds like there's a tap dance lesson going on in this house, kids, long story short, there is. I don't want to elaborate. I don't want to take away from the statistics, but you might be hearing a tap dance lesson going on concurrently. I hope you're okay with that. These are austere pedagogical conditions. Okay, errors in hypothesis testing. Hypothesis testing is an imperfect process. And there are correct decisions and incorrect decisions. Okay, so let me just check real quick what page I've got that on to make sure I'm using the same process. Okay, so here we have the decision regarding the null hypothesis. Okay, we either reject the null hypothesis or we fail to reject the null hypothesis. Okay, so we reject the null hypothesis or we fail to reject the null hypothesis. Hypothesis testing is very dichotomous that way. You kind of do one or the other. And up top, this is what I'm going to call, erase that, I'm going to call this the truth regarding the research hypothesis. So in some real sense, we'll never actually know it, but in some real sense, the research hypothesis can be true in some real sense, or the research hypothesis can be false. Okay, so there's 4 possibilities right there. So I could reject the null hypothesis, I could fail to reject the null hypothesis, and it could be a universe where the research hypothesis is true, or it could be a universe where the research hypothesis is false. 2 of these outcomes are what we call correct decisions. The best correct decision is this. The research hypothesis is true, so my idea was correct as researcher, and I rejected the null hypothesis, thereby supporting the research hypothesis. So this is a correct decision. And that is a correct decision in the researcher's favor. That's kind of the gold standard. This is kind of when you're doing research, what you're specifically shooting for. Here's a correct decision as well, even though it's less glamorous. Okay, in this world, with this correct decision, you fail to reject the null hypothesis. So just like with that last example with the student athletes, we fail to reject the null hypothesis, and the universe is such that your research hypothesis is actually false. There's no difference between mu sub 1 and mu sub 2 in the real world, and you fail to reject the null hypothesis, so you fail to support the idea of there being a difference. In the real world, this probably happens all the time. This is probably the most common thing that happens in research. It's disappointing, it feels like a waste of time, it can be humiliating, it can be deflating, it can be all those things. Get used to it, kids. If you're a researcher, you're going to develop thick skin. That happens, and if it happens, you have to say that's probably what happened. Here's 2 errors that can happen as well. You can reject the null hypothesis. Reject the null hypothesis, you remember that's a happy day. It's like saying, yay, look, I was right about my hypothesis. However, sometimes when you reject the null hypothesis, your research hypothesis is wrong. This is called type 1 error. Type 1 error is an error in your favor, is an error in the researcher's favor. Because of that, we usually don't call ourselves out on type 1 error. In fact, it's often other researchers, again, develop thick skin in this field, kids. It's usually other researchers that will accuse you of type 1 error or call your research out on type 1 error. That's an error in your favor. So if you think about an error in your favor in the real world, you usually don't dig around too hard, right? If you go to the ATM and you ask for $100 and it gives you 120, that's an error in your favor. You usually don't go into the bank and knock on the door and say, hey, here's an extra 20 bucks that I got. Probably should do that, by the way, just putting that out there. But you might not do that. When there's an error in your favor, we usually just are like, okay, I'm just gonna sort of turn a blind eye. There's another kind of error. We call this type 2 error. With type 2 error, I failed to reject the null hypothesis, so I kind of found nothing. But look at this, my research hypothesis was true. That is a sad story. That is a story where you were right, you did your research, and your research did not support that you were right, even though if you step back and look at how the universe really is, you actually were correct. You just happened to fail to reject the null hypothesis. There are many ways that the hypothesis testing procedure does not go correctly. There are many times that you get an outcome in your research, in your hypothesis testing, that doesn't really map onto one of these two correct decisions. That is the inherent nature of hypothesis testing, which is why I always tell students, don't use the word prove. When you're doing hypothesis testing, the best you're doing is supporting your research hypothesis. You cannot really overstate beyond that. So there's hypothesis testing for you kids. There's chapter 7. This has been Stats with Glenn.